Professor, you are so funny, ha ha ha.
Lucy, where are you? It's time to go to work.
I was doing yoga at the beach, Professor. Computer girls can go anywhere, anytime. I heard you said that you don't pay me enough, so I want more money.
Okay, Lucy, you got it. I'll give you anything. You the best. I'll give you a raise. Just don't join that computer girls union, okay? 'Cause they cause a bunch of trouble. But I'll give you a raise, okay? Remember, professors don't make that much money. Okay. All right, class. Remember from episode 2, okay? The laser and the interference pattern. Now here the issue is, as the laser passes through the two blades that are sharpened down to 100 micrometers, that's really small. The laser beam comes through and goes backwards. Yeah, it goes this way, it goes that way because it's curved, because no matter how sharp you make something, it's still round. Okay? There's no such thing as a straight edge. Okay, but Lucy's going to show you in the next segment here how the steel is so thin and the laser beam is so bright that it actually goes right through the steel. And that's how they weld with lasers. But yeah, the beam actually goes backwards, and that's why we get the interference pattern.
This is white light through a single slit. Rather, this is non-coherent white light passing through a slit. The slit is an adjustable closure made of two blades sharpened to a peak of less than 100 micrometers. The slit was adjusted down to a width of 0.254 millimeters or 10/1000ths of an inch. The source is 3 inches behind the slit, while the white screen the light is shining on is at 12 inches. The slit is 19 millimeters long. The slit acts like a lens in that the image here is approximately 30 millimeters long on the screen. As you move the source in or out from the slit, the magnification changes. Likewise, as you move the screen that the image is projected on, in, or out, the image magnifies. Of note, is there are no interference lines showing, as would be expected with a single slit, and non-coherent light. The slit acts just like a pinhole used in a pinhole camera. Pinholes are used by optometrists to determine refractive errors in a patient's lens. This is the same slit with a coherent laser light aimed through the slit. The laser is positioned approximately 6 inches behind the slit and the screen is positioned at a distance of 8 feet. Up close, at a distance of 12 inches, the light only looks like a thin stripe, but as you pull the screen back 2 feet, you begin to see what looks like interference patterns. At 8 feet it is quite visible. Of note, is that although the slit is vertical, the image is horizontal. Simple analysis reveals that the laser is a point source, and there are no light waves going vertically. What you are seeing is light being reflected off of the curvature of the sharp blades. Even though it is sharpened to 100 micrometers, the edge is curved. This is a magnification of the sharp edge of the slit. The edge is sharp enough to shave with. Next is an 800x view of the edge, done with a microscope. Notice that a blade sharp enough to shave with is still round. A human hair is about 1/1000th of an inch or 0.0254 millimeter. This edge is 1/10 the thickness of a hair. As a result, it will cut right into a human hair. Surgical stainless steel is sharpened to 5/10,000ths of an inch or 50 micrometers, and when magnified under a microscope it is still round. Next is a high-quality laboratory green laser. The beam is focused on a single razor edge. Because of its brilliance, it is difficult to see. The edge is vertical. As the beam crosses the sharp edge, it produces the horizontal line seen in the photo. The arrows point to the razor edge that is splitting the beam. The horizontal line appears because the sharp edge is still round, and the light reflects along the curvature, skewing a line. Next, we bring two edges together to make a slit, with the two edges only 10,000ths of 1 inch or 0.254 mm apart. We focus the laser on the slit. Again, the optical slit is vertical, and the beam scribes a horizontal line around the rounded sharp edges, but instead of a smooth line we see a broken line. This is called the interference pattern. Because the light is coherent, and the waves strike the screen at the same time, the frequency nature of light can be seen. The waves that projected on the screen are like the waves in water, they expand outwardly in an arc. Thus, the peaks and valleys of the waves cancel each other at specific points, creating the dark spots. We will see later how flat tangents curve. It is important to understand, this slit is two edges brought together. This produces two horizontal lines, one from each edge on opposite sides. Here is a magnified image of the edge with the laser beam being split. The flood of light, and I did not say photons, is so great that the steel atoms are excited to a point of transparency. In this image, a line is drawn in, to show where the edge is. Since laser light is straight, it does not magically wrap around the edge. In fact, the edge is so thin, and the waves so intense, that they pass through the steel. Any more intense by only a few watts, and the steel will melt, as is done with laser cutting and welding in industry.
Isn't that amazing? You wouldn't think that steel is transparent. But yeah, when it gets thin, the light goes right through it. Wiggles the front side, wiggles the back side, it goes right through. No matter how hard we try to make an edge that's square, there ain't no such thing. Everything's curved. When you get down to the smallest atom, it's curved. And the light, when it hits, it goes curved. It doesn't go straight. And later on, we're going to see that waves don't curve like water. They come out flat. How's that possible? If there ain't nothing straight in the universe, how is it that light waves are flat? Well, you're going to see that they actually flat. They're not curved like water waves. See, I told you we got snakes.
Good Lord, come on now, that looks like a rubber snake, Professor.
You don't believe me, huh? Okay. Okay, now, class, as we go along, I want you to start trying to get rid of the idea of a photon, okay? Because dark matter goes even smaller and smaller and smaller, so you can see how waves in dark matter can do the same thing that a photon does. There ain't no such thing as a photon, but later on we're going to see, okay? It's a long thesis, but we're going to get there. Photons don't exist. So then in the quantum world, the electron really does exist, okay? Because we can move them with magnets, and we can actually see them when they spark with lightning and spark, and you walk across the carpet and you touch the doorknob, you see the sparks, you see the electron. Okay? In the quantum world, they said the electrons spinning around and whizzing around, that would require an attractive force. And as you see, as we go on with the thesis, there is no such thing as attractive forces. It's an illusion, and magnetism is actually pushing in all directions. But we'll see now, we're going to break away from light, and we're going to break away from electrons, and we're going to go into some things that are going to be really eye-opening in combustion.
The idea of a thing called an electron, whizzing around a nucleus, being the structure of atoms, is difficult to imagine. It seems as though we looked up at the cosmos, and see the planets zinging around suns, and assumed that this must be universal, even in the micro-world of atoms. It has become more tangible through the ages with science experiments. We breathe invisible air that is made up of 70% nitrogen, 20% oxygen, 0.09% argon and 0.033% carbon dioxide. There are minor amounts of neon, helium, methane, krypton, hydrogen, and xenon which make up 0.04%. Many of these elements are floating around as molecules, which are denoted as hydrogen as H2, oxygen as O2, and nitrogen as N2. Uniquely, argon is a standalone atom. Once you see these elements as liquids rather than gas, it becomes more believable. All gases can be chilled and liquefied. One of the easiest experiments to show the reality of atoms is to take a vessel of salt water and place inverted test tubes in the vessel. Into the test tube you place a carbon electrode connected to wires, and you connect the wires to a battery. The salt water conducts electrons, and you will see bubbles rising from the electrodes that are captured in the test tubes. One of the tubes will capture hydrogen, and the other will capture oxygen, and the proportions are exactly what is expected from the formula, H2O, which is water. You see the test tube of hydrogen is twice the amount as the other which has oxygen. This process is called electrolysis, and was first discovered by Michael Faraday. You can carefully remove the test tubes, keeping them inverted, and pour the hydrogen, which is lighter, up into the oxygen, and carefully with a spark or other catalyst, ignite the gases, and they will quickly combine in combustion with a flash, and the release of heat and light. Watch out, and be careful because the test tube may explode. Water droplets will form on the glass, but most will rapidly evaporate. Now, with that experiment seen, you can believe that these separate elements actually exist. Whether they are structured in the manner that is described as protons, neutrons, and electrons is another matter. It was stated that it takes fire to make fire, and the previous example used a match to cause the hydrogen and the oxygen to undergo the reaction of combustion. It, however, can be made to react by increasing the pressure of the two separate gases, but it must be done rapidly as in a diesel engine. That is due to the heat produced by rapid compression will reach the point to cause combustion. If they are slowly compressed, they will not combine or combust. So, what is the action of combustion, and how has it been misinterpreted? Combustion Part 1. Again, let's see the universe as something simple, rather than complex, and also thermodynamics, which we will see makes perfect common sense. This is the current model of oxygen. This is only a representation. It has 8 protons, 8 neutrons, and 8 electrons. Hydrogen is the first order element and the lightest and smallest of all the atoms. It has only 1 proton and 1 electron. As described, protons have a positive charge, neutrons are neutral with no charge, and electrons are negative. Thus, you see the balance of protons to electrons as with oxygen there are 8 protons and 8 electrons. Hydrogen does not appear as a single atom in nature, it always hangs around in pairs. The pair is called a molecule and is named dihydrogen. As with our experiment earlier when we separated hydrogen and oxygen, and then poured the hydrogen into the oxygen, the two could exist side by side and did not combine into the compound water, until we added the catalyst of the flame. It could be an electric spark or even the spark of a flint. So, what is a catalyst? If it were the spark of a flint, we need to understand what caused the spark. It is the muscles in your arm that are oxidizing carbon from sugar, that move the striker, that made the spark, that will now ignite the hydrogen and oxygen. The point is that a catalyst is a reaction that causes a reaction that can be traced back. Thus, all events connect to a prior event and it takes fire to make fire. The hydrogen and oxygen combine to make water. In the process they give off heat and light, and it goes bang, as it collapses in space at the speed of sound. And yes, I said collapses in space. So, what happened?
Thank you, Lucy. Okay, we set this section up with an introduction to thermodynamics, and what's really interesting is how when you take the heat that's in this area, just like with a bicycle pump, and you push it into this area, you get times two, okay, because the heat goes up. Now, what happens in combustion, okay? We're going to deal with hydrogen and oxygen. And what's really amazing is that the two separate take up more space, and then when they're combined, they take up less space. And the weight goes down. The mass actually gets less. So if combustion is explosion, how come it got smaller? Oh, we found something really interesting. Watch this next segment. Thanks, Lucy. Take it away.
Most of the physics community see energy as being a unique entity. Professor Brainstein is breaking convention by stating that energy is something that matter possesses. Matter in motion possesses energy, matter at rest has potential energy. Molecules in motion are hotter than molecules at rest. When you pump up your bicycle tire, the pump gets hot. This is because you pushed molecules from a large space into a small space. The heat they had, which is their energy level, is suddenly pushed into a smaller space. If we started with 14.7 pounds per square inch, the pressure when compressed 10 to 1 would be 147 pounds per square inch. This is compressed air at 70 degrees Fahrenheit at 14.7 pounds of ambient air pressure at sea level, in a chamber of 10 cubic inches pushed down into an area of 1 cubic inch. The temperature will rise from 70 degrees to 700 degrees Fahrenheit. The heat, which is moving molecules of air, will rapidly dissipate into the molecules of the metal walls of the cylinder, making them more active, which makes the metal hot. Again, this is how a diesel engine works to explode the fuel without a spark plug. Thus, compression alone can be seen as stored energy and can again be used to do work. We use compressed air to run tools such as impact wrenches and air grinders and many others. So, when you compress air, it gets hot, but let it stand for a while, and the heat will dissipate into the walls of the cylinder. However, the compressed air is still compressed, and it can do work. The heat is considered lost energy. The heat of doing work dissipates entropically into space, but expand the gas after compression, and it not only gets cold, which is the process of taking on heat from other molecules surrounding in the environment, but it again does work. It took work to compress the can of air, but release the air to turn a prop that spins a generator, and the light bulb gets hot and gives off energy in radiant light waves and heat. It is necessary to explain. Heat is molecules in motion. Heat is a state of matter. It in itself is not a physical entity. Energy is not an entity but a state of matter, active or less active. Much like mathematics is metaphysical. It exists only in the human mind. Energy exists only as a state of matter's motion. There is no state of pure energy. Now bear with a few details as we analyze combustion. A hydrogen atom has a radius of 31 plus or minus 5 picometers. An oxygen atom has a radius of 66 plus or minus 2 picometers. A molecule of water is 95 picometers radius. Now, these are approximations at special conditions of pressure and temperature. Hydrogen and oxygen are compressible gases, but water is not compressible, and has the unique quality of expanding when it is frozen into a solid form, but continue to lower the temperature and it will again contract. Liquid oxygen is 1.141 grams per cubic centimeter. Liquid hydrogen is 0.07099 grams per cubic centimeter. Liquid water is 1 gram per cubic centimeter. So to prove the obvious, that when hydrogen and oxygen combine their mass comes down, please bear with some calculations.
Okay, this is called the combined gas law, okay? But it really is Joseph Louis Gay-Lussac, who was the originator back in 1778, okay? But Charles or Jacques Charles and Robert Boyle all got together, so that's what became the combined gas law. Now this is P, pressure, plus the volume divided by the temperature gives you a constant. I just make this up, okay? Now this leads us to what we call the pressure volume equation, okay, which is going to be so important in thermodynamics that you would think with combustion that all you got to do is look at the beginning pressure and the end pressure and the temperature transfer, and that's what combustion is all about. We find out that's not it. The pressure goes up, and in the experiment we're going to see that at the end it goes down.
In these next calculations, the professor is using the empirical value for the radius of the atom, and not using Avogadro's constant to calculate the number of atoms per cubic centimeter. There are many considerations when calculating how many atoms are in 1 cubic centimeter of liquid hydrogen and oxygen. The aforestated radius of 31 picometers for hydrogen puts the number at 4.195 to the 24th. That is 4.195 with 24 zeros. The real number is, as shown in this hypercalculation, oxygen is 434.788 to the 23rd, and the real number is as shown again in this hypercalculation. We need 2 to 1 hydrogen to oxygen, so we multiply the oxygen number by 2, and get 8.69577 to the 23rd, as shown in hypercalcs. That is the quantity of atoms of hydrogen that are needed. Thus, our cubic centimeter of hydrogen has too many atoms and must be reduced. We have the number of atoms over our requirement is shown. The exact ratio is shown, thus we must remove this ratio. Or simply multiply the volume by this hyper number. Thus, 1 cubic centimeter, which is 10 billion picometers cubed, which is 1.0 to the 30th times this hyper number, which equals this many picometers cubed. We then divided by the volume of the hydrogen atom, or the cube of 62 picometers or 238,328 cubic picometers, gives us this hyper-calculated number of atoms. Welcome to the tiny world of quantum mechanics. It can seem really small with really large numbers. Later we will see why the professor used the area of a cube instead of the area of a sphere.
Now, these equations have been tested over time, and time again they proved themselves to be true. The pressure-volume equation is kind of like the main one, and there's isochoric, isobaric, there's all kinds of different variations on the equation, and they all work. But you can figure the second volume just by taking the pressure and the volume of the first times the temperature at the end, number 2, and divide it by the original temperature times the final pressure. And you can figure out what the volume is. How big is that? So equations work. So they came up with a lot of nice variations on the equation, okay? And this one is called the isobaric, where I want to know what the final temperature is, T2, but and what I have is I know what T1 is, and I know what the volume 2, the second volume, and what the first volume was. And if I do this equation, then I know what the temperature is going to be, so I can figure ahead of time.
Now we can relax a bit and round off some numbers. Reducing our cubic centimeter of hydrogen to 0.207244 grams, our weight comes down the same fraction, so we multiply our 0.07099 grams times 0.207244 and we get 0.0147122. Thus 0.0147122 grams is what we need for an experiment in the combustion of hydrogen and oxygen. We are going to use 1.141 grams of liquid oxygen, that has a volume of 1 cubic centimeter, and 0.014712 grams of hydrogen with a volume of 0.2072444 cubic centimeter for a total of 1.1557122 grams, and a volume of 1.2072444 cubic centimeters. Liquid states are achieved at different temperatures. Hydrogen is a liquid at -423.182 degrees Fahrenheit, while oxygen is liquid at -297.332 degrees Fahrenheit. Now, Professor Brainstein uses Fahrenheit because most people in the Western Hemisphere and non-scientists can relate to how cold that seems. The equivalent temperature is 20.271 degrees Kelvin for hydrogen, and 90.188 Kelvin for oxygen. Again, it takes 2 hydrogen atoms and 1 oxygen atom to make 1 molecule of water. So, if we just add the weights of our full centimeter of oxygen and our adjusted portion of hydrogen, again we have 0.0147122 grams of hydrogen and 1.141 of oxygen per 0.0147122, plus 1.141, equals 1.1557122 grams. If we sum the volume of spheres of the atoms, using 2 hydrogen and 1 oxygen, it is 1,453,836.917 cubic picometers. The radius would be 70.276 picometers, but the atoms do not join in volume. The hydrogen is partially embedded in the oxygen, and is said to have a bent molecular shape. The listed radius is 95.8 picometers. Compounds of elements do not just sort of stick together, they sum. It is more like one slips into the other, making it swell. It is more like an oxygen atom eats 2 hydrogen atoms and its belly swelled up. Know that water is exactly 1 gram per cubic centimeter. This is because long ago, when the physics world began its measuring, they formulated many measurements around the nature of water. The gram, it was decided, shall be 1 centimeter of water at just above the freezing point, all the way to the boiling point. Water remains the same weight. Ahead of our experiment, we already know that after the hydrogen and oxygen are burned, or more realistically combined, we must precipitate or condense the now water vapor, and collect it to be measured. We cool it to the comfortable point of 20 C, or 68 F, or 293.15 K, and measure the volume and weight. Now, matter does not disappear, and is measurable by its weight and volume, so, the only solution that can be, is that we started with 1.155712298 grams that measured 1.2072444 cubic centimeters, and after combustion we have 1 cubic centimeter of water that weighs 1 gram. We lost 0.2072444 cubic centimeters of volume and 0.155712298 grams of weight. Really? So, let's begin our experiment. We will start with our very cold grams, 0.014712 of hydrogen and 1.141 of oxygen, and place them in a chamber, and slowly warm them up. We made our chamber exactly 1 liter of space internally, which is 1000 cubic centimeters. The hydrogen and oxygen will become a gas, but the weight will remain the same. Once the gases have evaporated into it, we will have each cubic centimeter inside the chamber containing 0.000014712 grams of hydrogen and 0.001141 grams of oxygen, for a total of 0.001155712 grams of the mixture per cubic centimeter. You can use your calculator to check as we go along. If someone finds a mistake, the professor will be embarrassed forever, but no pain, no gain. He will just blame his editor. Prior to the insertion of the hydrogen and oxygen, the chamber is evacuated to a near-perfect vacuum, so when the gases are inserted, it is sure to have measures of each gas that are exact. It is a near-perfect vacuum because a perfect vacuum is impossible. More on that later. Here again the professor will use Fahrenheit for those who relate to temperature, that way. The temperature in the 1-liter chamber would be controlled to 67.5 degrees Fahrenheit. This may seem strange, but remember that the liquid temperatures of these two elements are substantially different, and thus also their expansion ratios are different. Hydrogen expands 1 to 848, while oxygen expands 1 to 861. So that we have 1,000 cubic centimeters of our mixture to be at 14.7 psi, which is called standard pressure at sea level, or SP. It was found that this gas mix would meet our needed proportion at 67.5 degrees Fahrenheit.
Thank you, Lucy. All this attests here, okay, with the chamber, and this is called a thought experiment. We're trying to figure out what's actually happening in combustion. And what we find out is there's more energy released than just the transfer of volumes and the temperatures. We're trying to figure out, okay, is it just because these two, the hydrogen and the oxygen came together and they were at a temperature in the beginning, that's the temperature in the end? We find out, no, it's a bunch more. That the temperature goes way up. So what's happening? We're going to find out, but we got to go a little further into quantum physics before we find out actually what transpired. Love lasers, it's so much fun. Okay, this brings us up to the end of episode number 3. Things are, I know this is Physics 101, and pretty soon we're going to graduate from Physics 101 to 102 because it's really going to get interesting. Okay, it might get a little complicated because we're going to go deeper into the math. Okay, and we're going to apologize to Niels Bohr, okay, who invented the electron going around the proton and the neutron, which today's physics, if you got a physics professor, you need to clue them in that they're teaching the wrong stuff, okay, but it takes time. Everybody's going to wake up and figure out that we got it wrong, okay, and the Niels Bohr atom with electrons spinning around protons and neutrons, it's not real. Okay, and I'm going to say, Brainstein, who is Brainstein to tell us that that ain't real? Okay, well, you got to read the whole thesis, okay, but we're going to get deeper into it next episode. Episode 4 is going to go diving into the center of the atoms. We're going to get in there and see what's going on. Thanks for joining me.